Hi. The last session we have discussed about the features of SAC and SACXC, and we started with the assembler, and I have discussed about what is assembler, what is the role of the assembler, and what are the different functions of the assembler. So the basic two functions I have told you that one is converting or translating the mnemonic into machine equivalent. The second thing is assigning address to the machine symbol. Machine address to the symbol. So these two are the basic, the fundamental functions of the assembler. Okay. So now we move on to how the conversion is taking place. So before which we'll be discussing about some of the assembler directives that I have listed out in the previous session. Say it is a start, end, byte, word, reserve byte, and reserve word. And I also mentioned that about the pseudo instructions. Pseudo instructions are some of the instructions which cannot be translated into machine instructions. So these instructions only meant for providing information to the assembler. Let it be start, let it be end. So these are the some of the pseudo instructions. So what you are seeing in this slide is nothing but the SAC source program, so which is written in the SAC machine architecture. We have the assembly code here. So this assembly code can be given to the assembler so that it does the conversion. So if you could see the lines, that is line number 5, 10, up to 105, and we have up to 255. So there's a whole program. If you look at the line number 5, so it starts with the assembly directive start, and in the line number 255 you can see that the assembly directive end, which is denoting the end of the program. So the entire source program we have. Now the source program can be given to the assembler, so which does the conversion, so we can get the object code. Okay. So before moving on to how the conversion is taking place, so let me give some information about the assembler directive. Say for example, if you look at the start is one of the assembly directive which provides the information such as, which will be giving you what is the name of the program. You can make out, we can see copy over there, right? So the copy is the name of the program which is in the label field. So we can have label field, opcode field, and operand field. So label field, which we have copy, and in opcode field we have start, and in the operand field we have 1000. So it is meant for each instruction. Okay? So label field, opcode field, and operand field. And if you see the operand field, we have the number 1000. So as I already told you, mentioned that point, that when the program is writing a program, you would have assumed some address for the program. So thinking that the program will occupy the location 1000. So here the address is mentioned as 1000. So by seeing this line, the start will give you what is the starting address of the program. And one more thing is, this is the beginning of the program. So these three informations will be provided by the assembly directive called start. Similarly, when you look at the line number 255, end will give you, that is the end of the program. And in the operand field, if you look at, there is a symbol called first. Okay. So if you look at the line number 10, we can find first. So what is the meaning of first in the end is, by mentioning first over there in the end of the program, which is representing what is the first executable statement when the program is started executing. That is mentioned in the end assembly directive. So assembly directive end will represent that what is the first executable statement. And coming to the line number 80, right? The line number 80, we have the assembly directive called byte. Byte is used to generate or used to assign character constant to the symbols. Now, if you look at the operand, C followed by EOF. C represent character and EOF are nothing but the characters. So these characters are assigned into the label called EOF. The label is EOF and byte is an assembler which is used to represent that we are going to assign the character constant to the label EOF. And coming to the line number 85, you can see the assembler directory called word. And you can find the value 3 in the operand field. What is the meaning of this one is the word is used to assign or generate integer constant. So what it does, it assigns the constant 3 to the label 3. And moving on to the line number 95, we have assembly directory called reserve word, which is used to reserve number of words to the label. So in the operand field, we have the word as 1. So a single word is assigned. That means what? Single word is nothing but 3 bytes. As I already told you when we were discussing about the memory in SAC and SAC-XC, I mentioned that the consecutive 3 bytes will be forming one single word. So 1 represent one word. So one word is nothing but 3 bytes. So 3 bytes of storage is reserved for the label RET ADR. Similarly, the next line also, the line number 100, if you look at, again we have the reserved word 1. 1 represent one single word. And if you look at the 105, therein we have reserve byte. So reserve byte is used to represent the number of bytes to the are reserved, the number of bytes of storage are reserved for the label buffer. And the same thing which we can see in the line number 185, 190, and also we can have the byte into line number 250. So these are the some of the assembler directive which we can use it in our program. The rest of all are instructions. If you could see, we have the line number 10. We can see the operand field with the STL, JSUB, LDA, COMP, and so on, because these are the instruction set. So you got the clear picture about what are the assembly directives and what is the meaning of each assembly directives. Now we move on to how the conversion is taking place. Okay. Right. Now take the line number 5. As you know already, the line number 5 is having pseudo instruction. So this instruction need not be converted into object codes. That is why if you look at the last column, there is no value for the line number 5, that is instructions in the line number 5. So we are not creating object code. We don't have the object code for the instruction in the line number 5. So assembler doesn't create object code for this line number 5. Coming to the line number 10. So in the line number 10, we have opcode and we have operand. So what are the two functions I have told you when the assembler is converting source into object code? The first one is the mnemonic will be converted into machine equivalent. What is mnemonic? Opcode. What is opcode here? STL is an opcode. So STL will be converted into the machine equivalent. And the second point is the machine, the symbols will be assigned with the machine address. What is the symbol over here? That is in the operand field, RET ADR. So what is the value or what is the address for the RET ADR? If you look at the line number 95, you can see what is the address for RET ADR. So 1033. So now the value for STL is 14. Each and every mnemonic has corresponding value, the machine equivalent. I have shown you some of the slides where we could see the instruction sets, right? In the previous slides, where I have shown you the different instruction sets. So each and every instruction set has the equivalent machine value, right? So STL is having the machine value as 14. Now, what is the address for RETADR? The RETADR is defined in the location 95 and the address is 1033. So, what are the two functions of the assembler? One is the mnemonic will be converted into machine equivalent. What is mnemonic? STL is a mnemonic. It is converted into 14. And what is the next step? Assigning address to the labels. What is label here? RETADR is label. What is the address? 1033. That is how 141033 is the object code for the line number 10. That is the instruction in the line number 10. So this is how assembler is converting the source into object code. But here, how we derive this 1033? So the address 1033. So actually the program doesn't have the line number 5 nursery, the line and location. These two columns won't be there in the source program. Only the source statements, that is copy, start, 1000. These columns only will be available in the source program. So when it is given to the assembler, so assembler has to generate address for each and every line. How it generates the address? Because it knows what is the starting address. What is the starting address? 1000 is the starting address. So by assuming 1000 as a starting address, assembler will be assigning address to each and every line. Then only it does the conversion. So when it is assigning address for each and every line, how it performs the operation, I'll explain now. You take the line number 5, so that is having the starting address 1000. So the same starting address will be given to the line number 10 also. The reason is the start will not occupy any space. So obviously the starting address will be start from the line number 10. So the line number 10 will be having the starting address as 1000. And as you know, this is an SAC program. Okay. In SAC program, the instruction format will be taking 24 bits. That is nothing but 3 bytes. So each and every instruction will occupy 3 bytes. Since the line number 10, it is following the instruction format and it occupies 3 bytes. The starting address of this instruction is 1000 and it occupies 3 bytes. So 1000 plus 3, 1003 is the address of the next instruction. That is how in the line number 15, if you look at the address 1003. So how we derived this 1003 is 1000 is the address of the line number 10 and it takes 3 bytes of storage. So 1000 plus 3, 1003. 1003 is the address for the next line number 15. And again, line number 15 is following the instruction format. So 1003 is the address of that line plus it takes 3 bytes. So 1003 plus 3, 1006 is the address of the next instruction. Line number 20. Then line number 20, again, it will follow the same thing. So we get 1006 plus 1003, 1006 plus 3, 1009 is the address of the line number 25. Now, you have to see one thing. Here, 1009 is the address of the line number 25. Again, this instruction follows the same format, instruction format. So it occupies 3. So 9 plus 3 means it should be 12. But here, if you look at in the line number 30, you can see 100C. How does this C comes here is, when you are representing this address, address is mentioned in the hexadecimal format. Since we follow hexadecimal format, after 9, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, after 9, it has the value A, then B, C, D, E, F. Then after F, it will be 1, 0. So that is the reason when you have the address 1009 in the line number 25 and you are adding 3 to this 9, it will become 12. 12 is nothing but C. That is why 100C is the address for the line number 30. And similarly, 100C plus 3, which is nothing but 100F in the line number 35. And after line number 35, you can see 1012 in the line number 40. How you derived this? After F, then 10, 11, 12. So when you add 3 bytes to the existing 100F, obviously you're getting 1012. Okay. So then if you look at the line number 45, 1012 plus 3, 1015, 1015 plus 3, 1018, and so on. And again, if you see 1018, after that it will be 101B in the line number 55 because again hexadecimal. So this is how the assembler is assigning address to each and every instructions. And if you look at the line number 80, as I already told you that byte is representing, it is assigning character constant. How many constants we have? E, O, F. So there are 3 constants. So when it is a character constant, each character takes 1 byte. So since there are 3 characters, it takes 3 bytes. So if you look at the line number 80, the address is 102A. If you add 3 bytes to this 102A, you will be getting the value as 102D. That is there in the line number 85. Now, word line number 85, 102D, that will be having the word 3. So 3 is a constant. So it is an integer constant. For integer, it takes 3 bytes. That is why 2D plus 3, it became 30. When if you see the line number 90, the word is 0, then also for 0 is also value that will be taking, that is the integer constant that will be taking 3 bytes of storage. That is why line number 90, it has address 1030 that will be added with 3 means the line number 95, it has the value 1033 and so on. And same thing will be followed till the end. When you have line number 95, when you have the line number 95, we have reserve word. Reserve word means it will be reserving number of words. How many number of words we are having the line number 95? In the operand field, only 1. So one word is nothing but 3 bytes. So 3 bytes will be added. So that is why 1033 plus 3, which is 1036. That's there in the line number 100. And again, line number 100 has reserve word 1. So again 3 bytes will be added. So that's how 1036 plus 3, it will become 1039 in the line number 105. And coming to the reserve byte in the line number 105, it will be taking how many number of bytes we have, but it has the limitation up to 1000. If it crosses 1000, how many number of bytes you have given there, it will be considering only 1000. That is why 1039 is the address plus 1000 will give you 2039 in the location, in the line number 125. If you look at the line number 125, the address is 2039 because 1039 plus 1000 is 2039. This is how it takes the value. And coming to the line number 185, it is storing the hexadecimal 1 byte. So if you look at the address in the line number 185, 205D is the address of that line. And if you add 1, it will become 205E in the line number 190. 190. Same thing will be followed for line number 250 also. The line number 250, 2079. If you add 1, it will become 207A. So in this way, the assembler will be assigning address to each and every instructions in the source program. Once it does the assignment of address, then only we will be able to get the address for each and every line. So that is how, if you look at the line number 95, how this 1033 came, because assembler has generated address for each and every line, that is instruction. So if you know what is the starting address, then only assembler will be able to generate the address for each and every line. And moreover, it has to understand that each line, if this is the SAC program, each line follow the instruction format. So there is only one instruction format, so which follows the same, and it will be assigned the values based on that. So once it is done, then it does the conversion process. Now, if you look at the line number 10 again, so the first step is STL will be converted into 14 and RETADR will be converted into 1033. As we have already seen that the line number 95 has the definition of RETADR in the address 1033. That is how we put the address, assign the address for the symbol. So this is how the conversion is taking place. Same thing will be followed for all the remaining instructions except the few instructions. As I have already told you that we have seen the fundamental functions of the assembler. Apart from that, there is some more basic functions of the assembler also. Right? So those other functions also will be carried out by the assembler in few places. I'll show you that where are the places that the function will be carried out by the assembler. So if you look at the line number 15, 20 up to the line number 75, there is no change. The assembler converts, the assembler follows the two functions and it converts the source instruction into object code. But if you look at the line number 80, we have byte, okay, and we have the operand EOF. So if you have constant, right? If you have constant, what the assembler does is it will be converting into numbers. So if you look at the object code, in place of E, it will become 45. In place of O, it will become 44F. In place of F, it become 46. So these are the corresponding the hexadecimal number for EOF. So EOF will be converted into numbers. And if you look at the line number 85, in the operand field you have 3. Okay, the constant, integer constant. So integer constant will be converted into number. So number is same integer constant. That is why if you look at the object code 00003. And the line number 90, again, the constant is 0. So it is object code is having the value 000. And line number 95, 100, 105 doesn't have the object code because these are all pseudo instructions. And coming to the line number 185, so it is again the constant that will be converted into number. Since it is hexadecimal, same thing will be represented. So F1 is the code for the input device. So the same thing is mentioned over there. Similarly, in the line number 250 also, byte, that is the code. So that is why it is mentioned as 05. So this is how the conversion is taking place in assembler. So whatever we have seen, the same example, STL, RETR, that is converted into 141033. If you look at the instruction format, so the 1414, that is represented in the opcode field. So opcode field 1414 is represented as 0001 followed by 0100. That represents 14. And X bit is 0. Then again 1033. How it is represented? 1033. That is 001. For 0, it will be 4 zeros. For 3, it will become 0011. Again for 3, it will become 0011. So this is how we can accommodate the instructions into the instruction format. Now the problem with the assembler is when it does the conversion, as you could see in the previous example, wherein we have seen that whenever there is a conversion taking place, for the label or ETADR, it should know or it should assign the address for the label, for which it should know what is the value for RETADR. What is the value in the sense, what is the address of RETADR, where it is defined. So where it is defined, so we can see from the slide by easily what is the value for RETADR, because which is there in the line number 95, we can easily make out 1033. So as an assembler, when it reads the line number 10, so when it does the conversion, it has to move forward to the line number 95 and get to know that what is the address of the RETADR. So this concept is called as forward reference. Forward reference, what is the meaning of that is, when the symbol is used in the instruction, the symbol is not defined before the instruction. Instead, it is defined later in the instruction, because of which we have to move forward to reference the symbol. This concept is known as forward references. Because of forward references, the assembler will not be able to generate the object code in a single pass. So that is what it has to make jump instruction, because in the example, given example in the slide, LDA, LEN. So LEN is defined later, so it has to make jump instruction. Okay. Not only for the labels, even if you have any subroutines or the constants. So in those places, the assembler will not be able to do the conversion in a single pass. That is the reason it has to make two passes. So we move on to the two pass assembler. We have two pass assembler which performs the operation of conversion or translation from the source program into the object program. So for making object program, we have to perform we have to undergo two passes. The assembler has to undergo two passes, that is pass 1 and pass 2. So what is happening in pass 1 is, on pass 1, it assigns address to all the statement. That is what we have already discussed, how the assembler assigns address to each and every statements in the program. So for each and every instructions, it assigns the address. So that is the important step has to be taken by the assembler in pass 1. And save the values assigned to all the labels. Say for example, if in the line number 95, this RETADR is defined, and what is the address for that label that has to be stored, for which we need to create a table. And this will be used in the past. And perform some processing of assembly directives. As I already told you that we have different assembly directives like reserve byte, we have reserve code, we have byte, we have word, we have. So we need to know that what is the functions of assembler directives, what is the use of assembler directives. Okay, so that is what we have discussed already. So these all has to be done by the assembler directives. In pass 2, assemble the instruction. Actual conversion is taking place in the pass 2, and generate data values defined by byte and word. So what is the constant, whether it is a character constant or whether it is integer constant, based on that the conversion will be taking place. Perform processing of assembler directive not done in the pass 1. Whichever left out, that has to be done. Then finally, assembler creates object program and the assembly listing, that is listing files. So these two files will be generated from the assembler. One is object file and another one is a listing files, which gives the information, which provides some information. So these two passes have to be carried out in order to do the conversion or in order to create the object code. Okay, so how it is happening? What are the steps involved in pass 1 and pass 2 as per as it is given in the slide, as the functions which is mentioned in the slide. So with the algorithm, they are going to see how the assembler perform pass 1 and pass 2 functions. That we'll see in the next class.